special thanks to Kuma and Wafa. Otherwise, I wouldn't be able to do this talk. And so I should say that the first time I met her only 10 years later than Carlos did. So in 1995, it was a conference with me on geometric length, and she gave a talk, I guess, JLC, G. What's the title? I remember. And this is supposed to be the second kind of a companion talk to the one I gave to UPenn, which attended on the kind of the module story. UPenn, it was a demodule story of Riemann-Hilbert relations of demodules with Fukaya categories. And today I plan to talk about two demodules, different demodules from spectral curves, if you like, in the one-dimensional case. But then I realized that there are many people who didn't hear much of UPenn. And so then it will be a mixture of both demodules and two demodules. And at some point it will be confusing, but there will be a unifying theme, and it will be Fukaya categories, which we will see in most cases. So let me start. Well, that's the plan. You see just two parts. Demodules or HD modules, like families of demodules, connections. And the second part is a difference, storic DQ modules, difference equations. So I start with a very short reminder that in classical Riemann-Hilbert correspondence, it's a relation between connections on algebraic bundles on curves, in the simplest case with regular singularities. This is the round side by Mendelian H-theory terminology called by Carlos, and a representation for the fundamental group. It's a topological side of the story, Baker side, representations of this one of the complement of the projected curve to the marked points. So generalization to higher dimensions is a subject of the work of many people, most notably by Delin and Kasvara. And then it has led to the proof of Riemann-Hilbert correspondence as equivalent, as derived equivalence of certain categories of holonomic demodules and constructible sheaves, roughly speaking, so many people in the audience know precise statement. Holonomic demodules can have irregular singularities, and the latest versions of the Riemann-Hilbert correspondence, and but in the kind of simplest possible case, the functor which provides the equivalence Riemann-Hilbert functor, it assigns to a demodule, or in the right version to a complex of demodules. It's a sheaf of solutions. In the derived sense, it's a derived sheaf of solutions, like R home from the modules to the sheaf of functions from the variety. And so we see constructible sheaves, or complexes of constructible sheaves on one side, and some completely different type of objects on the other side. If we consider the characteristic variety of the demodule or singular support, for holonomic demodule, it's a Lagrangian, conic Lagrangian subvariety in the cotangent bundle, and we can take the micro support of the corresponding constructible sheaf of solutions. And so both of them are Lagrangian varieties, and therefore it's very natural, at least for people who like symplectic topology, to think that they are objects of some appropriately defined Fukaya categories. Category of A branes, in the simplest case for the cotangent bundle. In case if our D-modules system of differential equations allow to have irregular singularities, then these data should depend on some Stokes data associated with singularities. So then, in the end, we would like to have some Fukaya category and some Lagrangian subvarieties as objects in those Fukaya categories, which depend on Stokes data at singularities. I should say that we can consider everything in families to look for HD modules, or to be consistent with Qumran talk, I should replace H bar by zeta, because it's exactly, it has the same meaning. It's sort of a twisted parameter of the story. Now, working with HD modules like H connections, we can see not necessarily conic Lagrangian subvarieties, because if we have an HD module, then taking support of the corresponding coherent shift modulo H, we can see an arbitrary Lagrangian subvariety, even possibly, well, complex Lagrangian subvariety. Everything will be over complex numbers here, but even not necessarily smooth. If you want to...
Yeah, it's too loud. It's killing us. The microphone killing us. It's too loud.
It's too loud?
Yes.
So what do you want me
to
take it.
A little lower.
So,
halfway. Halfway.
Okay. Okay, great. All right. So, should I start from the beginning?
No.
So, in the language of differential equations, considering HD modules means that we're not only looking for kind of a characteristic variety, but we also look for something like the WKB asymptotics as H goes to 0. So in one dimension, this means that we would like to have both. We would like to have a D-module structure, like if H bar is equal to 1, and we also want to have a memory about the spectral curve, which appears as we go to the corresponding limit H equals 0, which is a Higgs bundle, but it can be analytically also thought as looking for the WKB asymptotics of our H differential equation. Now, I will be mostly talking about the one-dimensional case. There is a more general theory, but kind of a one-dimensional case is better understood, and it's kind of most transparent. Now, I will be talking about certain compactifications of the cotangent bundles, or partial compactifications, which we call, actually I forgot to tell at the very beginning, that it's part of the joint project with Maxim Kontsevich. And so we call these partial compactifications log extensions. And roughly speaking, the log extension of an, in our case, of an algebraic symplectic manifold. It's a Poisson. In general, it's a Poisson manifold which contains a symplectic manifold as an open symplectic leaf, and such that the symplectic form on that leaf has poles of order 1 on the rest, on the complement of this symplectic leaf to the whole thing. In the case of complex projective curves, so I would like to discuss kind of D modules with irregular singularities, holonomic D modules with irregular singularities, or the corresponding HD modules. So in that case, we start with a complex projective curves, a subset of singularities, and to specify the irregular nature, to fix the irregular behavior of the D module, let's define a singular term at a given point as a Puiseux polynomial. In general, it's a polynomial in rational powers, or going to some finite cover, we can assume that the powers are integer, and each the singular term appears with a multiplicity. So you can think of them as, if you look for the local solutions of the corresponding differential equations, so these things appear in the exponents. So the general solution is a product of some power, at least in the rank 1 case, in the power of the parameter, local parameter x minus xi, and some exponent. So this singular term is responsible for the exponent. All right, so that's the rest on this slide is what I said, that in the case of curves there is a canonical way to construct this partial compactification, which we call the log extension, but in general, in higher dimensions, there is no canonical choice of this log extension. In the case of curves, the details, all the details of that story can be found in our paper with Maxime, which also contains something related to Carlos' talk. But what I need is kind of a brief description of this, explicit description of this construction. It is achieved by a sequence of blow-ups of the fiber-wise projectivization of the cotangent bundle. So we add a copy of the original curve at infinity. So then there are also there is a copy of the set of singular points over there, and we start to make blow-ups. So this is the picture. So we start to make blow-ups at this point, at those points, and the rule is that at each step we make a blow-up either at the point where the standard symplectic form, or rather its pullback, has a pole of order at least 2, or if the point is smooth, or at the intersection of two divisors where the symplectic form has a pole of order at least 1. So then we have a chain of blow-ups, and in terms of Higgs bundles, it's a very transparent construction, because if, for example, x is a singular point, then the spectral curve goes to infinity when we approach this singular point. And in fact, we want to have some manifold where the spectral curve indeed intersects something. So there are, in one dimension, there are two possibilities to do that. One can work not necessarily with a cotangent bundle, which is a total space of the canonical bundle, but twisted by the divisor of singularities. But when you go to higher dimension, this kind of a blow-up story is preferable. So anyway, then we have T star of x just as an open symplectic leaf in a bigger variety, which is a Poisson variety, and this is our log extension. All right, now, so then in order to formulate the Riemann-Hilbert correspondence, so let me repeat again. Then I start with a finite set of points, a collection of singular terms with multiplicities, and also, since I would like to do everything in families, I fix a spectral curve, I fix a possibly singular complex Lagrangian subvariety in general in higher dimensions. And the condition is that the closure of this spectral curve, let me call it spectral curve, is compact. The closure in this log extension is compact, which means just that in this picture, when you look for the spectral curve, it intersects each of the exceptional divisors in finitely many points. That's it. All right. Then we can define two types of categories. On the Deram side, when the D-modules leave, we consider the category which is linear or polynomials, like families, of holonomic HD modules, like holonomic, for example, H connections on the curve, with prescribed singular terms, with prescribed C alpha at the given points. And as well as with a fixed spectral curve, when we consider the limit specialization as H equal to 0. So this is just exactly what I said. Now, similarly, we can forget about the spectral curve and consider basically if we work outside of the point H equals 0, like if we invert this parameter H, then our category is basically the category of holonomic D-modules. It's at each point, 0 point, it is equivalent to the category of holonomic D-modules with prescribed singular terms. Since going from, say, H connections to connections we divide by H, so it affects the singular behavior. All right, so then we have two types of categories. Now, this is the Deram side. Now, on the Betti side, we will see some Fukaya categories. So what kind of Fukaya categories? We will have two types of Riemann-Hilbert correspondences. One will be local, the other one will be global, but in both cases, they will be Fukaya categories, which are finite dimensional representations of certain partially wrapped Fukaya categories. So how it works with a little bit more detail. So we have a symplectic, complex symplectic manifold, the Katangian bundle, with a standard form. We can rescale the form dividing by the Planck constant, or we can do it even in twistor families, but I'm not interested in non-holomorphic behavior today. So then we have a family of complex symplectic manifolds. Now, what kind of Fukaya categories we are interested in? So we can convert holomorphic symplectic form into a real symplectic form and the B field. So then the Fukaya categories will be taken of now real symplectic manifolds, but I will also take care about the symplectic, the B field. Now, again, two types of categories, the local one and the global one. The local one will be associated with a small tubular neighborhood, a Stein neighborhood of the spectral curve, and it's basically of a topological nature, because in this small neighborhood there are no pseudo-holomorphic disks taken in any generic complex structure, and globally, of course, there can be such pseudo-holomorphic disks. All right. Now, again, these categories, global and local, they will be the categories of finite dimensional modules, which means A infinity functors to the bounded derived category of to the category of complexes, to the derived category, bounded derived category of vector spaces, but the categories from which I will consider such functors, they are partially wrapped Fukaya categories of two types of real symplectic manifolds. One is this, just a cotangent bundle, but the Lagrangians will be required to have a nice behavior near the blow-up divisors. And this much simpler category, in a sense, of local nature is just a partially wrapped Fukaya category of a tubular neighborhood of a given spectral curve. So let me start with the global Riemann-Hilbert correspondence. So some objects of these are Lagrangians with compact, now real Lagrangians, not complex, real Lagrangians with compact closure in this log extension. For example, spectral curves are good for that, they are objects. And also each Lagrangian is endowed with a finite dimensional local system. Now, A-infinity structure is a bit more subtle because it should involve some Hamiltonian flows. There is an explicit description of appropriate Hamiltonian flows. Just for kind of for completeness, I mentioned that this Hamiltonian flow is of such a nature that for an open part of every exceptional divisor, so this difference is a union of normal crossing divisors, which are P1s, and on the open set, which is just R2, this Hamiltonian floor acts by translation along some real line. All right, so I do not want to spend time on these foundational questions because they are not quite settled for partially wrapped Fukaya categories. So what we get in the end is a kind of generalization of Nadler-Zaslow Fukaya category for the cotangent bundle for those who know the subject. And what is good about this, at least for the cotangent bundle, then the answer can be expressed in terms of constructible sheaves. But in general, if our symplectic manifold is not a cotangent bundle, then appearance of constructible sheaves seems to be artificial, but the Fukaya categories are kind of more fundamental in general. All right. So that's what I mentioned, that there will be two types of correspondences. Local, when the spectral curve is fixed, and the global one. So the global one is a sort of easier to prove, although because of these foundational questions about partially wrapped Fukaya categories, I prefer to formulate it as a conjecture. So, but basically it's a reformulation of the irregular demodule correspondence formulated by Delin and Lagrange in 80s. So then the conjecture is the following one. the category of holonomic d-modules on the curve with prescribed singular terms at fixed points is equivalent to the global Fukaya category, which I mentioned previously. And this is equivalence of triangulated infinity categories, provided I extended scalars here to a Novikov field. Probably there is some convergence in this global story, at least when I consider the Planck constant to be sufficiently small. And so probably it's enough, it suffices to work not over the Novikov field, but over some field of germs of neuromorphic functions at the origin. Okay, so this is what replaces constructible sheaves. Although, in order to prove this conjecture, one way to prove it is to identify both sides with categories of constructible sheaves. So it's easier to do it with Deligne-Malebranche, because in that case one considers constructible sheaves on the curve with a micro support which belongs to the union of certain halves of cones. So this is a picture. So it's not the full cone, but it's just positive part of cones. So it's a union of positive conormal bundles. These are positive conormal bundles, no negative parts, positive conormal bundles of some co-oriented real analytic curves about singularities. It's not an algebraic, it gives non-algebraic stratification of this Riemann surface. And these curves, in this picture, these curves, they can be explicitly described in terms of given singular terms. These are just images of small circles about singularities under these maps. All right, so then in the end we have the Lagrangian, singular Lagrangian subvariety, which is a union of the zero section of the cotangent bundle and these positive conormal poles. I consider, so there is an appropriate category of Lagrangian branes considered by Nagler and Zaslow in this particular case, because it's a cotangent bundle. But it's equivalent to the category of, in the right sense, to the category of constructible sheaves with the prescribed micro support. And the same category can be, if you look carefully at Deligne-Malebranche, you can identify it with the Durham side. So then basically using the classical results, we can fill in some details about wrapped Fukaya category, partially wrapped Fukaya categories, we can prove this conjecture. All right, one more thing. If you look here, you will see that this picture defines some knots, Legendrian knots at the contact boundary at infinity. And these knots can be seen on the Durham side when we look in the way how the spectral curves intersect, these, how it behaves near these exceptional divisors. So as I will formulate probably the conjecture later, there is a contact isomorphism of the contact boundary of the cotangent bundle near infinity. So when all these knots will live on the kind of infinite, in the infinite three-dimensional sphere, if you'd like, with a similar story in the log extension of the tangent bound. So anyway, this is a global story. As for the local story, local Riemann-Hilbert, we fix a spectral curve, then the corresponding partially wrapped Fukaya category lives over integers. There are no disks. But there is a relation. Again, I formulate everything in the conjectural way, although there are some hints on how to prove it. So there is countably many Stokes rays. Actually, these are defined by the periods of holomorphic symplectic form with respect to the relative classes H2 of the cotangent bundle. So I consider kind of disks with a boundary on the spectral curve. So, but outside of these Stokes rays, when my Planck constant doesn't belong to either of them, we conjecture that there is an embedding of the local category to the global one. And if the Planck constant is sufficiently small, in a very small disk, then if you assume kind of convergent, then this one will be a kind of a deformation of this one. So in general, it's a deformation of the Novikov ring. So we allow some disks with a boundary on the spectral curve, and if you take into account all of them, we get the whole thing. So then the local, this category of holonomic HD modules with fixed spectral curve and fixed singular terms is equivalent to the local Fukaya category. And this equivalence is compatible with the global equivalence. Outside of Stokes rays, the local Fukaya is embedded to the global one, and obviously, if we forget, if we take a D module and put, say, H equal 1, then we get just a D module out of the HD module. So then we have a global Riemann-Hilbert correspondence, so it can be arranged into a commutative square of equivalences of categories. Now, one more thing in favor of Fukaya categories in this Riemann-Hilbert story is that the inverse Riemann-Hilbert functor, which means constructing the module out of some Betti-side object, can be obtained by sort of a family Floyer type construction. So, like in the simplest case, you consider a family of cotangent fibers intersecting the spectral curve, and you take the home from the spectral curve to this moving family of cotangent fibers in this Fukaya category. So it gives you a all right. So this is kind of a short account of my talk at UPenn. So now quantum torus, or QD modules, if you like, or DQ modules, just distinguish them from HD modules. So it's a story about difference rather than differential equations. So in dimension, this theory is much less general in the sense that at best it can exist only on toric varieties. For example, on C star of n. That's the best we can do. No even on the cotangent bundle, an arbitrary complex manic. So this is a definition of a quantum torus. So I take Q to be, say, absolute value of the parameter Q to be smaller than 1. And I consider difference equations on C star of n, modules of finite type of a quantum torus. There is an analog of the cotangent bundle in the story. It's just C star to the power 2n. One can, I mean, it's quite easy to develop basics of the theory of DQ modules, mimicking the definitions for D modules, like the Bernstein filtration, and subsequently the definition of holonomic DQ modules, and like inverse image. Anyway, some very basic things. This was done by Sabak in 90s. But the Riemann-Hilbert correspondence for these different modules, for DQ modules, is much less understood, even in the one-dimensional case, which different equations on C star, the corresponding Stokes data were proposed relatively recently by Ramis, Aloy, and Zhang in 2009. And I will recall or rather reformulate their result, because they consider only q-difference connections, and I would like to take into account torsion as well. Torsion modules as well. All right, so similarly to the story of the modules, so I illustrate everything first in one-dimensional case, which means I consider quantum spectral curves. Now we can naively define the sheaf of solutions, and considering difference equations, which something like f of qx equals some function defining x product with f of x. So the corresponding sheaves of solutions are coherent sheaves on the corresponding elliptic curve. So let this q whole denote the category of holonomic DQ modules on C star. In order to formulate the Baker side of Riemann-Hilbert correspondence, I will need the notion of anti-Harder-Narasimhan filtration of a coherent sheaf. So if I have a coherent sheaf on the elliptic curve, which is filtered by real or rational numbers plus infinity, so I will say that the filtration is anti-Harder-Narasimhan if the slopes of the subsequent quotients goes in the wrong way, opposite to Harder-Narasimhan filtration. In particular, the very first quotient is has a maximal slope, it's a torsion. All right, so then this is the Riemann-Hilbert correspondence for DQ modules. So the category of holonomic DQ modules on C star is equivalent to the category of coherent sheaves on the elliptic curve, which are endowed with two anti-Harder-Narasimhan filtrations labeled by rational numbers plus infinity. So these filtrations should be thought of as Stokes data for our difference equations at 0 and infinity. So we have C star, we have two fixed points on CP1, 0 and infinity for the natural action of CP1, or if you like for the corresponding toric variety, and Stokes data appear in these compactifying divisors, like 0 to infinity. And these, for Deligne-Malgrange in usual D modules, Stokes data are also certain filtrations. And here, these are filtrations which satisfy anti-Riemann inequalities for both 0 and infinity. All right. This slide is about the inverse to this Riemann-Hilbert functor. So how to describe the DQ module corresponding to a given coherent shift which is endowed with two filtrations. The idea is to pull it back to C star. So we have an equivariant coherent shift in C star. And then filtrations impose certain growth conditions from the sections of the shifts. So the corresponding DQ module will be a vector space of analytic section of a coherent shift, which is a pullback to C star of our given coherent shift in the elliptic curve. So since it's a pullback, it carries an action of the quantum torus multiplication by the variable x coordinate on C star and the shift which comes from, which corresponds to the action of the second variable y. And moreover, as I just said, we impose some conditions on the sections of the associated graded factors. In particular, so basically two conditions that, for example, if we consider torsion part, then these are sections which have compact support, which means that they vanish near infinity. The pullback of every point is a geometric progression, but we consider only such sections which vanish at the infinitely many points, at infinity or at zero, depending on the corresponding on which filtration we take into account. And also some growth condition for the remaining portion. So then the construction, as you see, very explicit. This inverse Riemann-Hilbert functor is very explicit. And the funny thing, but useful, is to see that this construction can be also seen in terms of family Fourier homology. If we fix the spectral curve, we can do it here in one dimension. So yeah, n equal 1, we have C star square, we can fix the spectral curve inside of C star square and perform to have not only global Riemann-Hilbert correspondence which is in the blackboard, but also local Riemann-Hilbert correspondence in a completely parallel way to the case of HD modules. And these correspondences can be understood from the point of view of family Fourier homology. One should take a family of C stars which are transversal to the spectral curve and take the Fourier homology in the appropriate Foucault. All right. Now it's the main purpose of my talk is to formulate the conjecture in higher dimension. So now I'd like to slow down a little bit because before our work there was no even a conjectural answer to the Becky side of the Riemann-Hilbert correspondence for holonomic DQ modules. And nice thing about that is that it's a mixture of three types of geometries. Of tropical geometry, as you will see from the answer, symplectic geometry and algebraic geometry. Okay, what are the data? On the tropical side, I start with conic polyhedral Lagrangian subset in R2N. So which I would like to think as a sort of a Lagrangian family. It's a finite union of rational convex cones of full dimension, such that their interiors do not intersect. Also, I fix the branch of the argument function for the standard holomorphic volume form. So I will proceed as follows. First, I will assume some kind of data as black boxes and will formulate the Riemann-Hilbert correspondence. And then I explain how to construct these data. So these data are mentioned here as A and B. There are two types of things. One is a local Fukaya category associated with this conic Lagrangian subset, and the collection of functors to complexes. Each functor corresponds to the cone which appears in the decomposition, in the presentation of this Lagrangian as a Lagrangian. Now, suppose that we have this data, A and B, Fukaya categories and functors. Then every cone, since it has a dimension n, is contained in the unique rational hyperplane. And to every such a hyperplane, we associate some abelian subcategory and the derived category of this abelian variety, power of nth power of my elliptic dot. Now, the choice of the argument function, it's basically, it corresponds to the shift, to the action of the group Z, to the shifts in the derived category. There is an action of the central extension of the group SP to NZ, central extension by Z. So this group acts on the derived category, so kind of a mixture of Fourier-Mukai and shifts, integer shifts of complexes. The same group acts on the set of pairs, the Lagrangian, rational Lagrangian subspace in R2N, and the choice of the argument. We can shift an argument by a multiple of 2 pi, and we can act by the element of SP or on the Lagrangian subspace. In particular, we can take an arbitrary Lagrangian subspace and using this action make it into a standard one. So in this standard one correspond to the very simple T structure, it's just coherent shifts with zero-dimensional support. With finite support. So then if I have an arbitrary pair, rational subspace and the branch of the argument, just using the transitive action of this group, we can make it into a standard. So modulo this Fourier-Mukai and shifts, I have my category, abelian category, is a subcategory in this derived, in the derived one, consisting of coherent shifts which have finite support. Before I formulate the the conjectural Riemann-Hilbert correspondence, just a couple of things about the intuition, which explain the previous data. So if I write the C star of 2n, my analog of the cotangent bundle, if you like, as a product of these two things, and if I think that I want to compute the Fukaya category of this torus, then it should be a sort of a tensor product of the Fukaya of this. And this explains the appearance of polyhedral Lagrangian in the previous discussion. And the Fukaya category of the flat torus. Now, applying mirror symmetry, homological mirror symmetry to this second factor, I will have a derived category of coherent shifts of the corresponding abelian variety. All right. So then, having, let me recall that another piece of data are some functors, and then thinking about the Fukaya category, intuitively thinking of the Fukaya category of this as a sort of a product of these two things, I can apply the functor to the first tensor factor and get an object here. So then, on the Baker side of the Q Riemann-Hilbert correspondence, instead of constructible shifts, and in the demodel case, I will have coherent shifts on the abelian variety in agreement with n equal 1 case. So that's a statement. The category of holonomic DQ modules on the torus is equivalent to the category which is described as an inductive limit of the categories obtained from the local Fukaya categories by applying the functors which are my data B to the first tensor factor. All right, so this, roughly speaking, these are, this category consists of coherent shifts on my abelian variety, which modulo Fourier Mukai and certain integer shifts have finite support. That's the intuitive picture of the base on the beta side. Yeah, that's on the beta side. And now, in the remaining few minutes, I will comment on the definition of the local Fukaya category and the functors. As for functors, it's easy, just taking the fiber of the constructible shift with a smooth point. So most interesting part, and most symplectic part, is the local Fukaya category associated with my, it's not quite tropical Lagrangian, because I consider it as a Lagrangian subset, polyhedral Lagrangian subset. But you can make it into a tropical cycle because there are some balancing conditions in the question, in the story. But anyway, so I have this polyhedral Lagrangian subvariety L, and what's the definition of this local Fukaya? So let's look at the sphere at infinity. It's all the same sphere, more or less the same. And then my Lagrangian defines a Legendrian subvariety, polyhedral Lagrangian subvariety in this compact 2n-1 dimensional sphere. Now let's choose a generic irrational n-dimensional subspace in R2n. Then at infinity it does not intersect my Legendrian because all this is rational, this is irrational, but it defines an n-1 dimensional Legendrian sphere. So if n equals 1, we have a three-dimensional sphere and Legendrian limit at infinity. So now this is a proposition. Probably I should also formulate it as a conjecture, but it's almost proven. That if I consider a complement in my contact manifold to this Legendrian sphere, then it's contactly isomorphic to some spherical bundle for the standard ball. So the point is that I would like just literally to reduce this story to Schender, Riemann, and Zaslow story for the cotangent bundle. Because if we assume that proposition, so we are now again in the cotangent bundle case, and the local Fukaya category can be described in terms of constructible shifts. And it can be done explicitly, but the answer is very much similar to what we have in the case of D-modules. So we just take our Legendrian, or rather let's identify it with the Legendrian at the contact infinity of the cotangent bundle, and let's project it to the base. Then we have a stratification of the base, which is similar to the stratification of my Riemann surface by real analytic curves, which we had in the case of D-modules. So we have some constructible stratification, and the base is the ball. That's in this proposition. And so then I consider the category, again, everything is derived here, the category of constructible shifts with the micro support, constructible shifts on the ball, with the micro support, we belong to the union of positive conormal bundles of these strata, and which are zero, homologically zero near the boundary, which are quasi-isomorphic to zero near the boundary of the ball. So then this gives, well, depending on whether you are symplectic topologist or not, it gives either the answer or the definition of the local Fukaya category, this F, which appears with which appears in this set of data which I needed for the definition of the Betti side of Riemann-Hilbert correspondence. And again, the functors are just fibers of the constructible shifts and smooth points. Now, this is a pictorial illustration of the geometry in the case n equal to 1. So the ball is just an interval, so strata correspond just to finitely many points, and these are positive conormal bundles. So my subvarieties, they are co-oriented, similarly to the case of analytic curves on Riemann surfaces. They are co-oriented, so then each cotangent fiber, they take either the part which goes up or the part which goes down. But anyway, this is a picture, and I consider constructible shifts, or complexes of constructible shifts, which quasi-isomorphic to zero here and here, and with a micro support which belongs to the union of these things. And the remark is that, again, if we settle all foundational questions about the partially wrapped Fukaya categories, then we can avoid this use of constructible sheaves and contact isotopy with the Katanzian bundle and work directly with the partially wrapped Fukaya category of our Lagrangian subvariety. Well, it's I believe this is the final slide. It just repeats what I said before about the actual construction of 2D module using the family of Floer homology type procedure. There are many interesting questions here. In particular, everything is modular with respect to the modular transformation of the quantum parameter Q. It does not follow from what I said before, but interestingly enough, this modularity can be explained using this family of Floer homology construction. And just kind of a couple of final words. All that is part of our project with Maxim, which is called the homomorphic Floer quantization, and which puts on the same footing this kind of fields, like Riemann-Hilbert correspondences and exponential integrals of the type similar which appear in Qumran-Stokes. So also there is something about wall crossing in the story. So basically local Fukaya categories, they are well defined at some Stokes sectors, and when we cross Stokes rays, there are some instant-on corrections which can be explicitly written down in terms of holomorphic disks with a boundary on the spectral torque. And in order to construct the global object, one need to solve some Riemann-Hilbert problems. In the case of 2D modules, quantum Riemann-Hilbert problems, which are very much similar to those which Qumran wrote, this TBA type Riemann-Hilbert. Thank you. There are no questions, so I don't need to use.
Thank you. Okay, thank you very, very much. You saved me from freezing.